All right, thank you, Robin, and thank you all for staying until almost the last session here. So today I'm going to be talking about what are almost certainly the most practical algorithms that we currently have for simulating quantum chemistry on a small fault-tolerant device. And this is work done in collaboration with Craig Gidney, Dominic Berry, Nathan Wiebe, Jared McLean, Alexandru Paler, Austin Fowler, and Hartmut Evan. All right, so at Google, we are interested in building a fault-tolerant quantum computer. And we have some idea of what that might look like. It's going to take a while, but we're aiming for, maybe the first platform that we think might do something useful would look something like this. Might have 100,000 to 1 million superconducting qubits on a planar array, and we'd be aiming for something like 10 to the minus 3 error rates, and we hope we could do something like state distillation in roughly 150 microseconds. And so, a common conversation is we sort of tell this to executives at Google who inevitably respond with some question like this, how much is that going to cost? And of course, we don't really know the answer, probably a lot. And eventually the conversation turns instead into this, which is, okay, well, what interesting, classically intractable problems could you solve with that? And how quickly could you solve them? So for a device this small, you're not going to have a lot of logical qubits. So applications like factoring and many problems in optimization are not that enticing. One of the most promising applications we do have is simulating small but still classically difficult problems in quantum chemistry. There's obviously been a lot of work in this field, but surprisingly, there's only 2 papers to date which have gone all the way to the level of Clifford and Teagates and really assessed how long a fault-tolerant device would take. The first paper came out in 2017 in PNAS, and they looked at a particular problem relevant to simulating nitrogen fixation, an important problem in chemistry. And there was about 108 qubit instance, and they found you need 10 to the 14 or 10 to the 15 T-gates. So the authors of that paper had in mind that they might have a topological device, and if they were to try to have a particularly small device with just one factory for distillation, they had in mind that this topological device could do state distillation in 10 nanoseconds. And with those numbers, you could do this in maybe weeks. But for the architecture we have in mind, state distillation would take 150 microseconds, and so that algorithm would take us centuries. So it just wouldn't be practical for us. Which is why I'm excited today to talk about our recent work, which looks at a different problem, and I'll talk about the nuances between how the problem's different. It's still a quantum chemistry problem, larger than 100 qubits, and classically intractable, where we can solve it in with about 10 to the 8 T-gates. So on the topological device, that would reduce time from weeks to seconds, and on our architecture, that would reduce from centuries to hours. So we already kind of did this sort of background about quantum chemistry in the previous talk, so maybe I'll go through this pretty quickly. But systems of interacting electrons, they're very hard classically, and they're important. It takes a long time to simulate molecules. There's good applications like making better OLEDs for the pixels in your pixel, or scientific applications like what's going on with superconductivity. So in the case of chemistry, the Hamiltonian is pretty straightforward. We're interested in the electronic wave function, and basically the electrons interact with each other and with the nuclei through the Coulomb potential, and they have kinetic energy. So that's the Hamiltonian. And we're typically interested in energies of these systems so that we can compute reaction rates, which teaches us a lot about chemistry. And typically, the way you do this within a fault-tolerant architecture is to prepare eigenstates by applying phase estimation to some good initial guess. So I want to briefly, in order to understand the context of this work, I'm going to briefly rehash some stuff I spoke about last year at QIP, which is the relationship between Hamiltonian representation and cost. So often, or historically, people have used Gaussian molecular orbitals to represent the Hamiltonians for quantum chemistry simulation, because these are very compact single particle basis functions, and you don't need that many qubits to represent molecules with high accuracy. But the problem is it leads to very complicated Hamiltonians with end of the 4th terms. Last year at QIP, I talked about the fact that if you use some simpler basis functions, which are related to the plane waves, you get much simpler Hamiltonians, only n squared terms, and this is going to help a lot of quantum simulation algorithms, basically. So this sort of basis function is very good for simulating periodic systems, so crystals, which are periodic in 3D, or graphene, which is periodic in 2D. But it's not quite as good for, say, molecules, where the wave function's dying off exponentially. In fact, it's asymptotically equivalent to any other choice of single particle basis, but there's a big constant factor difference. In practice, you'll need a lot more plane waves than Gaussians in order to represent these systems. And so as Dominic talked about, and he presented our recent work about simulation and first quantization, that's not such a problem, because in first quantization, we could take the number of plane waves to be huge and just sort of make basis error thing in the past. But that is not what we're talking about here. We're talking about a maybe slightly more practical algorithm for the near term. So I like making tables like this. Here I'm comparing over the years how certain papers have improved the gate complexity, the best algorithms for quantum chemistry. So, at first people were mostly looking at Trotter and using second quantized Gaussians. But at some point we switched to the Taylor series looking at LCU methods, which gave some improvement. And then basically, starting with this paper, which I spoke about at QIP last year, we started looking at plane waves. And there have been some more results using plane waves, including the ones that Guang Hao presented and Dominic presented. So these last three papers are really what's being discussed at QIP this year. These two were in the previous talk, and you have one which in second quantization has n squared complexity, but quite frankly the constant factors there are very, very large due to details of its implementation, and also the spatial complexity n log n is kind of a problem for a small fault-tolerant device if n is something kind of big that would be classically intractable. In first quantization, you could take n, of course, to be very, very big, but it's still a more complicated algorithm. So today we're actually talking about this algorithm with n to the third scaling, which for some of you might be less exciting because it's not asymptotically better than these two. But in terms of what you can do on a small fault-tolerant device, the constant factors here are much lower, and so it's advantageous in that way. So in fact, I can actually give you the exact constant factor in our scaling, which is that if we have a Hamiltonian with one norm lambda and we're using n plane waves, our t count is exactly 24 square root 2 pi n times lambda over epsilon. And I should note this is the first time we've ever been able to report the t complexity of any chemistry algorithm like this because, well, in Trotter methods, it's more complicated, basically. Okay, so what we're typically trying to do here again is we're interested in sort of sampling in the eigenbasis of the Hamiltonian from some initial classical guess state psi. And so here's some notation. Basically, we're trying to sample the eigenvalues of the Hamiltonian with a probability that has to do with the overlap of the initial state with those eigenvectors. So we can do this with phase estimation. And for the purposes of this talk, it's going to be helpful for me to just say that if you have a unitary W like this, that's sort of a sufficient condition for you to be able to apply phase estimation. And so what this unitary is here is it's a unitary who encodes in its eigenvalues, in the phase of its eigenvalues, it encodes the eigenvalues of the Hamiltonian as some function. And I'll explain in a minute why I'm describing things that way. But if you have a unitary like this, then you could show that in general the cost of performing phase estimation is the cost of implementing this W over epsilon divided by the derivative of this function, which is a function of the eigenvalues of the Hamiltonian. So the thing that we typically do is much simpler than what I'm saying. It's just time evolution. That's what's been done in a lot of papers. And in the case of time evolution, the cost would then become basically the cost of applying the time evolution operator to within epsilon for time t divided by epsilon t, and then you choose the t to minimize this cost. And I think a lot of you are familiar with that. We're going to use something slightly different. We're going to use this quantum walk operator, which you can sort of think of as being time evolution under the arc sign of the Hamiltonian scaled by this normalization lambda. And in this case, the cost is going to end up being the cost of implementing this quantum walk here times lambda divided by epsilon. And up to errors from circuit synthesis, there is no error in realizing this quantum walk. Unlike Trotter, there's not like some number of steps that needs to be refined. It's just exact, which is kind of interesting. So the focus of our paper is really realizing that W, compiling circuits for it, and going all the way down to the surface code. So our result is that we can implement this quantum walk for both the Hubbard model and chemistry at complexity n plus log 1 over epsilon, which I believe, but don't know for sure, is asymptotically optimal for that purpose. And then the number of times you have to repeat it scales like this lambda, which is n squared for chemistry, and n for the Hubbard model. So how do we actually realize this thing? Well, we use basically cubitized quantum walks. So a lot of you are familiar with expressing the Hamiltonian and accessing it as a linear combination of unitaries. So we're going to do that. And basically, the quantum walk that we use is kind of prescribed by the qubitization ideas from Guanghao. And so we'll talk about it in terms of these two oracles, which can be qubitization oracles. So you have one circuit which selectively applies of one of these unitaries in the linear combination of unitaries to the system, controlled on this register that indexes the terms. And we have another one which prepares a specific state on this index register with amplitudes that are proportional to the Hamiltonian coefficients. And then this lambda thing is the same as it always is. It's this one norm. So basically, this circuit tells you how to realize the controlled W, which realizes the quantum walk I was talking about that we need for phase estimation. 2 applications of prepare, 1 application of select. Pretty straightforward. So there were a couple papers in late 2017 that both essentially pointed out and kind of worked out some of the details of the fact that you can, in fact, just prepare eigenstates by performing phase estimation on this thing, and it kind of works out how you would expect. There's a couple details there, but the point is that by performing phase estimation directly on the quantum walk instead of the time evolution operator, we don't need to synthesize the time evolution operator using quantum signal processing. So we don't use quantum signal processing, and that does save us some overhead asymptotically too, so that's nice. But of course, we're not finished. So I've recently encountered a couple reviewers on a couple papers who seem to think that qubitization plus chemistry is an algorithm. But it essentially isn't. Qubitization is a framework for querying oracles to affect evolution. And I suppose there's a very obvious way to implement these oracles, but it would give you a terrible algorithm. So to really make good algorithms, there's really an art in figuring out how to realize these state preparation and selection oracles, and that's what I'm going to talk about, and that's a lot of what our talk is about. So the first oracle, select, I'll go through kind of quickly here because I think it's less interesting. Our Hamiltonian, when expressed as qubits, looks something like this. And you basically need to find some way of associating the index register with the different terms. So in this case, we have these qubits theta, u, and v, which just kind of pick out which of the 5 terms here I'm talking about. And then we have p alpha and q beta registers, which say what qubits the term is acting on, and that indexes it. So basically, I have to implement a unitary that does something like this. Now, there's n-squared terms in the Hamiltonian, and they have locality of up to n, and I have to control on some register. So the kind of brute force solution that qubitization might prescribe here would be something like n to the 3 log n complexity. But of course, that's not what we do. We have a much nicer solution with t count that's exactly 12n and uses only log n additional ancilla. I'm not going to go into the details of it. I don't really have time. But I'll say that one of the key primitives here is one that essentially realizes this operation, applying a Clifford operation to qubit p controlled on a register encoding the binary value p. And basically, to kind of get some intuition for what we do, imagine that we used n extra ancilla qubits. We could map p from binary to unary in in n complexity, and then we can just control the Cliffords on this one hot unary register, and that would give us a linear t complexity result. But we have used n ancilla. So our construction is basically about figuring out how to stream bits of that unary register without explicitly realizing it and using only log n ancilla. So I think the prepare techniques we developed are ultimately some of the more interesting and I think impactful results that will people will care about a little bit more broadly. So again, this is our Hamiltonian. You might think that this is the prepare operation again. We're trying to realize this state, and you might think that a brute force solution here. There's n squared terms. You could figure out a brute force way of doing that in n squared log n gates. But you might kind of realize, hey, this Hamiltonian, the parts of it with n squared terms, the Coulomb and kinetic operator, they're actually translationally invariant. And so I've actually written the coefficients here as p minus q to kind of make that point. And so there's only, and the part that's not translationally invariant has only n terms. And so the point is that there's only n unique coefficients. And you could kind of find some clever ways of then realizing this thing with n log n complexity instead. But we do even better than that. We get our t complexity is 6n plus log n. And there's a couple steps here. One of the things we do is we introduce a circuit that we call QROM, which does, it's a circuit for doing this operation, which a lot of you have probably thought about before. It's kind of like QRAM, but we can't write to it, so we call it quantum read-only. Also, unlike QRAM, we have explicit circuits for its construction, and I can tell you exactly what its T-complexity is. And it is that if you need to load in entries from a database of size L, the T-complexity is 4L. And kind of interestingly, the cost of this is independent of the size of the entries. And so you can kind of see our paper for how we do that. But basically what we do is we start trying to prepare this state. Again, we're trying to do this. We start with just an even superposition, and we have some ancilla. And then we apply QROM to load into the superposition some values that we call alt-L and keep-L, which are values associated with L. And then what we do is we do something we call coherent alias sampling, which is now kind of appearing in some other LCU papers as well. But basically the idea is to create the state that we want by swapping the registers L and alt-L according to a probability that is given by keep-L. And and basically what we end up with is a state that looks like this. It's almost the state we want, but it's entangled with some junk. But which often that's not okay, and there's not an easy way to uncompute the junk. But it turns out it's okay for our purposes, because the whole point of this prepare is just to make a register you're going to control on. And then you're going to uncompute prepare. And because you're only controlling on that register, the phase errors will commute across the controls and then just get uncomputed. And so it doesn't actually matter, and we can kind of think of the task at hand as trying to prepare a classical probability distribution, which is why this works. And so you might be wondering, okay, what are alt-L and keep-L? So if this is the probability distribution we're trying to realize, so the y values are the values of the WL, or the square root WL, and the x-axis here is just the different values of L, then what we do is we have an efficient classical algorithm we actually provide Python code for, which sort of repacks these values so that each value of L, has sort of total amplitude exactly 1 over L, which is, what we have here. But it's associated with two values, like the orange one is alt-L and the red one is L. And the probability, or the keep-L, is just sort of the ratio of, the colors here. And so that all works out, and it gives us this, the fact that these log factors are additive, which is quite nice, because we need very high precision. So there's a whole lot of other circuits in our paper, and I don't really want to talk about that. So the rest of this talk, I'm going to talk about compiling to the surface code and the resource estimates. So, this is basically an AND operation, TOEFL applied to a 0 qubit. It comes up a lot in our algorithm. And if you're kind of familiar with error correcting codes, if you actually want to realize this in a fault-tolerant way, all these operations, you have to, you have to basically specify, groups of stabilizers that you measure to implement this operation. And so you have these, topological diagrams like this, or kind of like assembly for the surface code, basically, to help you figure out the resources that would actually be required. You might say, oh, this doesn't look so bad. There's not so much to measure. But wherever there's a T-gate here, you have some monstrosity that looks like this or something, which is a T-factory that is kind of, there's a part that sticks out of the screen and attaches to this horrible T-factory, which is a place where you distill magic states. And first of all, it's very, very slow. It takes, maybe 150 microseconds to distill these magic states. And it also consumes a huge number of physical qubits. So this kind of factory, a braided factory, which is sort of the best thing that had been fully worked out when we put out our paper originally in May, in our context, meaning given our error rates and the size of circuits we're talking about, is something like 150,000 physical qubits for one of these. That's a lot. And that means that, if you have a small fault-tolerant device, that's possibly bigger than your memory. You probably want only one of these or just a couple of them. So you're mostly going to be doing these distillations in series, and it's really going to be the bottleneck for your algorithm. And it's kind of crazy because this is an AND gate, and it's taking 0.6 milliseconds, which is 10 million times slower or something like that than what it takes classically. So you really got to watch out for these. Fortunately, as we heard about on Monday, there have been some recent improvements. So this is our previous braided T-factory, and this is the lattice surgery T-factory that Daniel Latinsky spoke about at QIP on Monday. And also, Craig Gidney, and with the help of Austin Fowler at Google, has been working on some other variants of this, which are very helpful in certain circumstances. In particular, our algorithm really benefits from Craig's construction of a CCZ factory, which is distilled states for CCZs as opposed to T-gates, and we're bottlenecked by CCZs in our algorithm, so that's good. Because the last surgery CCZ constructions from Craig, they require 3 times fewer qubits and are about 4 times faster than the previous braided factories. But still, this stuff takes a while. So let's say you thought maybe a week was a reasonable amount of time to run a calculation, and you were going to just have one CCZ factory, then it would still take, basically you could do about 10 to the 9 CCZ states in a week. So if you only want to have one factory, maybe try staying under 1 billion CCZs. So of course, what we did is we, looked at compiling this stuff to surface code gates. And we did that both by hand, meaning we took like the bottleneck primitives and basically Craig and Austin just kind of fiddled around with them and figured stuff out. And also with an automated system which was developed by Alexandru Paler. And we basically, first of all, by compiling all this stuff down, we showed that we could, woohoo. But also, we were able to confirm the bottleneck is in fact state distillation, because when you really try to optimize T complexity, you very much run the risk that that you'll sort of over-optimize it, and basically the Cliffords at some point do catch up, but we're not near that regime, and that's good. And also the hand-optimized ones and the machine ones, they were actually kind of similar too. One catches optimizations, the other doesn't, and vice versa. So again, because our algorithm is about using plane waves, the benchmark systems we looked at were periodic systems, crystalline solids, diamond, graphite, LIH, metal, silicon, uniform electron gas, that kind of thing. And actually, the only system-dependent part of this algorithm is just the value of the one norm, how many times you have to kind of repeat this stuff, which is actually fairly insensitive to the particular instance that we were looking at, in the sense that we could mostly just talk about the cost within a factor of 5 or 10 in terms of just how many orbitals or qubits is the system register. We also estimated resources for simulating the Hubbard model. That was a whole part of our paper too, deploying this stuff for the Hubbard model. But I didn't have time to talk about it so much in our talk. But we focused on a regime of the Hubbard model that is challenging, very challenging to look at classically. And so here are some numbers. We have this table in our paper, but the table in our paper used the braided T factory, so it's maybe, this is updated with the recent CCZ factories and stuff, so it's maybe 3 or 4 times better. But we're pretty excited by these results. So here, the P is the error rate that we're assuming. So for Hubbard model and electronic structure instances with over 100 orbitals, we could get away with using less than, well under 1 million physical qubits in the surface code at 10 to the minus 3 error rates, and the runtime would only be a couple hours, which is a big improvement from needing tens of millions or hundreds of millions or something, and centuries or whatever. And in fact, it scales pretty nicely too. I mean, we could go up to electronic structure instances of 1,000 orbitals, and at 10 to the minus 4 error rates, we'd need just a little over 1 million physical qubits. So yeah, we're kind of excited about this. I might have been scared by the last talk a bit and gone pretty quickly here, but we've come to the final discussion. So just to put this stuff in context, the prior state of the art, again, was simulating something like FOMOCO, a very important molecule at 108 qubits, but with our architecture, it would have taken centuries. By sort of changing the problem and developing new algorithms and new ways of compiling these things and so forth, I just discussed that we can do, say, 128 qubit crystalline material simulations in hours, or we can do 1,000 qubit ones in essentially days. And we're excited about that, and we should be, because it means there are cool things we can do with a small device. But FOMOCO is still not one of them, because you still can't, you really probably would need hundreds of thousands or millions of plane waves to do FOMOCO, just because of the way the basis error works, basically. And so this is not an appropriate algorithm for small molecules, just sort of in the same way that the first algorithm talked about in the first talk was not appropriate for small molecules. They both aren't. However, one way out of this, which is essentially what we did, and Dominic spoke about our work in the previous talk, is you could look at algorithms in first quantization. And in first quantization, you can have gate complexity that's only logarithmic in n, gate complexity that is n to the 1/3, and space complexity that's logarithmic in n. Actually, I very much would like to know, and I think it's a great open question, whether it's possible to have gate complexity that's logarithmic in n, which would be very cool because you could actually exponentially suppress basis errors. The basis error goes as, the error suppressed is 1/n, by the way, regardless of the basis. So anyways, I think that this is actually kind of a pretty promising approach for simulating, real molecules. You could just use 1 million plane waves or something, and it would probably be practical to do, but not quite this practical. There's still some complicated things about that algorithm. But we do intend to compile and figure out exactly how long it will take. Another question that I have is, if we're just kind of pushing on what are the very first things we can do with a fault-tolerant device, we're well under 1 million superconducting qubits required to do cool stuff now. And I wonder if we can get under 100,000, and I suspect that we can. And I think that will take people pushing on both the development of better surface code, gate realizations, better T-factories, and better algorithms too. So that's my talk. This is our paper. And I want to thank all my collaborators again, especially call out Craig, who we call Craig the compiler, Craig Gidney at Google, and Dominic Berry, who you saw in the last talk. Both these guys really helped a lot in this paper. But of course, everyone made valuable contributions. Again, also Nathan Weeb, Jared McLean, Alexandra Paler, Austin Fowler, and Hartmut Nevin. So thank you.
All right, so we have time for questions. Who wants to start? Do you also want to plant a question in the audience like Dominic did?
Do I want to plant a question?
Actually, let me get started maybe.
Okay.
Oh, good, we have somebody in the queue. But okay, let me get started now that I said I'm going to say something. So people often ask me, why are we studying quantum algorithms for a Hamiltonian simulation? And then it's like, okay, there's a lot of reasons, but one of them is that, Hamiltonian simulation is BQP complete, so we're not going to find classical algorithms for this unless, our entire industry collapses. Can you also say something about, why we think chemistry is a great application? Can we, for example, prove that it's BQP complete in some sense, or is it some other reason?
Okay, there's about its BQP completeness, there's a lot of things you could kind of argue. So, often, I guess, just to clarify something that I know you know, Robin, but a lot of people are confused because you have these models of interacting electrons, which are formally QMA hard, but really the context in which we study chemistry is that with a promise, and the promise is that you can generate some, classical approximation, essentially, that has some strong support on the eigenstates of interest. And so, that's usually the problem we study, and we study that because in practice, the methods of quantum chemistry are they're often kind of qualitatively right in a sense, especially about things like chemical structure and stuff. If the mean field solutions didn't have any relationship to the ground state, then the chemistry you learned in high school would just have absolutely nothing to do with reality and would be pointless. So I think it's a testament to chemistry as a science that there are some classical approximations that give you some of the information. Although doing things like computing rates, you really need to be very accurate, and you just can't do that classically. I guess another argument about BQP completeness, though, is simply that nature exists, and unless you speculate there was some crazy resource state at the beginning of the Big Bang, and I think I heard, I've heard other people, maybe Scott Aronson or other people, talk about this argument for many years. But, unless you speculate there's some crazy initial state, then it's all just time evolution unfolding everything. And, so if there's molecules that exist, they got there somehow. So you can imagine mostly just kind of simulating how they came into existence, and then you have them. And in terms of how we think it's hard classically, people have studied electronic structure at probably a couple chemists in every department in the world for 100 years, and there's still a lot of juicy problems that we just can't get sensible answers to. So it just seems hard by experience, really, classically that is. I think. Yeah.
Thanks for the great talk. So trying to understand the relative merits of the two different basis sets, which I don't really understand yet. So I know that you went to the plane wave basis set because it had a smaller number of terms. There's got to be some disadvantage in going to that basis set?
Yeah. So the disadvantage is that the molecular orbitals are very compact, meaning you don't need all that many of them to represent the molecule to high precision. This is especially true with like small single molecules where the density of the wave function is dying off exponentially as you go away from the molecule. Having molecular orbitals that are sort of centered on the nuclei is really pretty good at that. Whereas plane waves, they're diffuse. They're also periodic. So they're kind of what you need for periodic systems, infinite periodic systems like crystals and stuff like this. In fact, they are asymptotically equivalent because the hard part in really converging the wave function is resolving the electron-electron cusp, which happens at all points in space. The Gaussians are centered on nuclei, so they're good at getting the nuclear cusp, but not the electron-electron cusp. But the constant factor is big. I mean, you may need 100 times more plane waves to treat some molecules, maybe even 1,000 times more than you would Gaussians. Now, for periodic systems, you just use plane waves. That's what you use. And so there are some systems that are naturally described by plane waves, and you don't need some crazy amount of them. And so basically, if you're in second quantization, I don't think you'll ever really do molecules with plane waves, but you'll do materials. However, in first quantization, plane waves are cool because you can use 1 million of them.
So part of the same question is, does the weight of the terms in the Hamiltonian change at all when you go between the different basis sets? So
that's
if I'm
a
interested
good
in, say, the
question.
L1 norm of the coefficients and nothing else.
That's what. So it doesn't change much. It changes a little bit. So really, we're actually working with rotated plane waves, which it's like a Fourier transform of plane waves, which you'd think is a delta function, but it's a finite basis, so it's some kind of like sinc function. But the point is that this is a very spatially local basis set, and in some sense, you would think that kind of minimizes the L1 norm of the Hamiltonian, but empirically, asymptotically, you see that the norm in second quantization is maybe like n to the 2.5, and it's n squared in the basis that we're looking at. So it's a bit better, but it's not a huge difference.
More questions?
So one of the fun aspects about the surface code is that these braids are squishy and you can deform them to trade space for time and so on. How much is that possible here? I know that in the T factories, for example, there's some restrictions with post-selection and so on, but how much are you able to trade off space for time here?
Well, so you can always trade off space for time, but eventually you're going to run into different bottlenecks. So, for instance, if we wanted to go 5 or 10 times faster, I think we could essentially almost achieve that just by building 5 or 10 times more T factories, which would essentially, multiply the space by 5 or 10 times. But more than that, and I think you're likely to start to hit Clifford bottlenecks, although we'd have to do the analysis more carefully to be sure. And then you might be less possible to do that, but there's other things you can look at. So I think a good parallelism up to another factor of 10, and
Other questions? We still have time.
In the previous talk, Dominic mentioned state preparation based on Grover and amplitude amplification, and in this talk you mentioned state preparation based on alias sampling.
Yeah.
So how do these two compare?
Well, we have to prepare states in both cases, but basically the state we're preparing in the case of this talk is essentially a less structured state than the one we need to prepare in Dominic's talk. That is a state with very specific structure. It's like the sum over k of 1 over k times the ket k. And so in the context of Dominic's talk, you could combine the Grover thing with some other kind of clever insights to make the complexity almost negligible. But here, you can't do that. However, for preparing kind of the arbitrary databases, and here we need to prepare an arbitrary database of size L, essentially. I think that the alias sampling thing we introduced is basically the best thing out there. The Microsoft guys had a nice paper out a few months ago, which it built on some of the ideas from the alias sampling, and also had some clever ideas about how you could use dirty qubits to make it a bit better too. But for us, that wouldn't have asymptotically changed the complexity, because then we would have been bottlenecked by select instead of prepare.
All right, maybe let's thank Ryan again.